diffraction, and we'll have another group quiz today, and then both the ones from Tuesday and Thursday will be due this evening. As an upload. So I hope that you had a chance to look at the ones on Tuesday, because you have 3 more of those today. And I saw some of you were just kind of taking off. So I guess maybe it's because there wasn't an imminent quiz or something, but you really do have to stay up on this stuff. And so I do have solutions for those when we get to it. Where we left off last time is with the double and multiple slit relationships. And what we saw is that the sine of theta is equal to m lambda over d, where we have this kind of a slit separation distance. We have a screen over here, and we have a pattern that is associated with the different m values. So this might be m equals 0, m equals 1, m equals 2. So these would be the bright spots. Halfway in between them, we would have the dark spots. So this is for constructive interference. For destructive, which is the dark spots that you would see on the screen, you have sine theta equals m plus 1/2 lambda. So this gives you an integer multiple of lambda over 2. So this is the dark spots for destructive interference. So we're going to have a lab on that this week, and this is a simulation right from the lab that we can use to help illustrate this idea. Say that we have a point source coming in like this, and here we'll have them come in as plane wavefronts. What you can see is happening is as the waves travel through the slits, you can think of it as being a bunch of point sources on each one of these wavefronts. They're interfering with each other. And so if I increase the frequency a little bit and decrease the slit width, we can see this interference pattern perhaps a little more clearly. You can see here that this point source and this point source, we get to this point, we have a bright spot. And so anywhere along here is constructive interference, where along there is constructive interference, along there is constructive interference. So that corresponds to what we were showing here to be our m equals 1, m equals 2, m equals -1, and m equals -2 spots. So this would be along this line here, that would be m equals 1. This would be m equals 0. This would be m equals -1. You can see we're getting constructive interference along those lines. And then here, this would be destructive interference, and so those would be dark spots. So those would be these points here, where the 2 point sources are canceling out. And so that gives rise to the -1/2, 0, +1/2, +1, -1. Okay, so we're getting constructive interference along the integer, and along the half integers, we're getting destructive interference, or dark spots on the screen. So the plane wave is coming in, we're blocking most of the waves so that we just have point sources essentially from these two that are interfering in order to produce either constructive or destructive interference. So if we go back to the picture of all of this, you can see what's going on then with the can see where we're at then with this picture, where this would be m equals plus 1 in this case, let's say, and then this d sine theta would be lambda. That's the difference in path length between this distance, r2, and r1. So that's our delta r, that's our path length. We want that to be m lambda for constructive interference, but that difference in path length, if we just drop this perpendicular down and do a little bit of geometry, we see that this angle and that angle are the same, so that the angle that we're measuring from the horizontal is equal, if we put that in here, because it's the same angle, then this delta distance here, delta r, is d sine theta. And so that means that this wave has gone through one complete cycle and is ready to pick up where this wave left off. So when this starts, then that's when this one starts. And so they both get to the screen at the exact same spot. And so that's the geometry of it, and then we saw last time how you can get bright and dark areas. Are there any questions about any of those results? Yeah.
So you said the constructive interference parts on the graph that you do on the board, where those little points are. You said the leftmost apex is the destructive and the rightmost is constructive?
I don't know what you mean by leftmost apex.
Right there on the board where you wrote constructive, like those little
These
points.
are the destructive.
Those are
That's when you've got no brightness.
Gotcha.
So on here, those are these points. No brightness, no brightness, no brightness, no brightness. So that's what you're going to see in the lab. It's a bunch of things that look like that. And then this is bright, bright, bright. So it's m equals 0, m equals 1, m equals 2. So that's looking at it from 3 different perspectives.
Gotcha. And then those bright ones are the constructive interferences?
Yeah. Any other questions? Okay, so we did that. And then last time we also showed that we can get a more peak distribution with multiple slits, so that the different individual peaks for different components of the wavelength don't overlap. Because we might not just be looking at one wavelength. We might have, and this is more general, have a source that has many different spectral components to it. And so that's the whole basis of spectral analysis. You take the light and you analyze it by breaking it up into its individual component wavelengths. And so that then gives rise to a more peak distribution here. And with a more peak distribution, we left off last time with a multiple slit. We saw that the red and the blue had a different angle. This is theta blue, this is theta red. And we still have the same relationship, sine theta equals m lambda over d, but in this case we had to figure out the slit density in terms of d. So d then was 1 over the slit density. And what we were able to show is that we had about a 17-degree sweep in the angle and going from red light to blue light. And so that's basically where we left off last time. I just wanted to review that because these are a lot of interesting geometrical relationships that we're trying to pull together all at once here. Are there any questions about any of this? So that's old stuff. Let's do some new stuff. What happens if we also are interested in the wave energy that happens because of the width of the slit itself? And we can see that here. The slit itself has a certain width, and so that means that there is a whole, we can think of along the slit as there being a whole series of point sources, and that they can interfere with each other within the slit. And so that's a different kind of diffraction. That's what we call single slit diffraction. And so what we've been looking at so far with multiple slit and double slit This is all good because it helps us analyze the spectrum of light. What is bad is the single slit. Bad, bad, bad. Because what it does is it creates limitations on how well you can analyze your data. Okay, so this also occurs in double slit diffraction. Clearly, because each slit has a finite width. So this is an additional interference effect. Due to interference along the width of the slit. And so what does that look like? Well, you can see it a little bit here, although it's not, doesn't come out super well, but along the center, there's a big peak. Okay, so there's constructive interference there. But here along this line, you get destructive interference. And so this is what we could call our m=1 dark spot. So this is what we call our central interference maximum. This would be -1 down here. And then up along here, you can see that these waves are kind of interfering. This one's interfering with that one, this one's interfering with that one, that one's interfering with that one, that one's interfering with that one. So you can set up a bunch of complementary points in which you get destructive interference at certain angles. Okay, and so this would be our m=+1 dark spot. And when we do a more detailed analysis of this, which I have written out for you on this handout, here's the double slit. And so this is just a sample calculation like what we did in class last time. It's on the second page of that. The front page was what we did before with telescopes and microscopes. So last time, this is just kind of a summary of some of the things we covered last time. But then here, this is also a summary of what we covered last time. But then with multiple slit, we see how much better the peaks are aligned. Did a quick calculation here for delta theta with slightly different numbers from the example I did in class. I just changed the slit density and I worked the same problem out that we did in class. So you can see it for two different slit densities, how that works. And then here we go to single slit. Okay, and so in the single slit, you can set up a bunch of interference patterns that are associated with different combinations of the point sources from the slit. And so this gives rise to a whole set of different values for destructive interference. So you can go through these if you want. I don't have time to go through all the details of that in the lecture, but I can write down the result. And the result follows from what I've written here. So that result for single slit is sine of theta is equal to m lambda over A. So it looks a lot like our double and multiple slit diffraction pattern relationship, but with B replaced by A. So this is our slit width. But there are some differences. One, n can't be equal to 0, and this is the equation for dark spots, not for bright spots. Okay, and so what we end up getting then is a pattern that looks something like this. Okay, so that is our single slit pattern. This is our double slit pattern. The single slit pattern tends to be more spread out because the angles have to be bigger for the single slit pattern because A is smaller than D. Okay, we're dividing by a smaller number here. That makes the angle bigger. So this pattern is really spread out. That's the single slit pattern. The double slit pattern is regular. It has an m equals 0 in here. So in here you'd have m equals 0. But that would correspond up here to our central interference maximum. And then here you'd have m equals plus 1. But over here, this might be this would be plus 1, m equals plus 2, m equals plus 3. So we can see that this pattern is much more confined or squeezed up because the angles are smaller. That's sine theta equals m lambda over d. But because d is much, much greater than a, these angles are much bigger. Okay, and so if we just look at it by itself, the single slit pattern looks something like this. So this is what you're going to see in lab. Although it'll probably just be kind of a cross-section of this. It won't be long like this. But you'll have a central bright spot. Here. So this is your central interference maximum. So if we plot this up like this, the intensity versus time, or versus distance, is going to be something like this. This would be m equals minus 1 dark spot, m equals plus 1 dark spot. But in the 0, we have the central interference maximum. Like that. And then it drops off, but with lowering intensities. So this would be m equals minus 2, m equals minus 3. This would be m equals plus 2, m equals plus 3, etc. And so we get a bright central spot, but then here we get the positions of the dark spots. And so this destructive interference can wipe out our double slit diffraction pattern in certain places. And so this was actually what you were asked to do on problem 3 in yesterday's or Tuesday's lab. Is basically this pattern is superimposed on that one. So if you've got this pattern is a really big pattern, and this pattern is a really small pattern, then what you're going to see is this kind of bright spots, then you're not going to see anything there. And then you're going to see less bright here, and then nothing there. Okay, so this double slit is going to be basically what the single slit is. Like this, but then it's going to be gone in these regions where the single slit takes it out. Something like that. And so you get less here, then not quite so bright in there, and then nothing there, and then less bright out here, etc. And so this is the kind of data that you're going to get in lab. You're going to see the double slit pattern in here, but what's going to be tempting for you to want to do is say, oh, well, it's this bigger pattern that I'm measuring for double slit. But no, the bigger single slit pattern is wiping out some of your double slit data. And so your best data then comes from the central interference maximum, because that's where the single slit pattern and the double slit pattern both have a maximum intensity. Okay, and so that's why this is a complication. It's something that messes us up. It's not something that we like. It's something that is a limitation to our ability to analyze the data. And so let me try to show you how this would look with one of our simulations. And you also get a chance to play with these simulations in lab. Okay, so this was our double slit pattern. But now I'm going to turn this into a single slit. I can do that over here by just turning two slits to one slit. Now I've got a single slit pattern. Okay, now what if I widen that single slit a little bit, like that? By widening the single slit, we can see more of the interference that is associated with the different point sources along the source, creating constructive and destructive interference. So what we're seeing here then is the central interference maximum. But then here, this is your m equals 1 dark spot. Here's your m equals minus 1 dark spot. And there are other ones. But sometimes when you go to m equals 2 or m equals 3, the angles are so big that it goes to 90 degrees. So that's something to watch out for, is that you don't always get a projection on the screen if the angles get too big. But this is your single slit pattern associated with the width of each slit. But then superimposed on that, you have the double slit pattern, which is the interference between the two slits in which the waves are producing constructive interference as point sources between those two slits. And so then that's just both effects added together. So this becomes smaller here, and then goes out like that, and this becomes basically 0 there, and 0 again out there, etc. Okay, so I hope with what you can see here and what I've written down, plus what I've been able to show on the board, that kind of makes sense. Are there any questions? All right, let's next take a look at a problem where we've got both patterns together, and let's ask if D equals 1 millimeter in a double slit grating. Then let's find the slit width of each slit. If the m equals 2 bright spot from double slit diffraction is wiped out by the m equals 1 dark spot from single slit diffraction. So you might think here that we would need to know the wavelengths. But let's just see what happens if let's do a graphical thing first, just to see if we can picture what is being asked for in this problem. First of all, I'm going to draw the single slit pattern because it's the bigger one. Bigger in angle. So this is our single slit. So this would be M equals 1 dark spot, M equals 2 dark spot, M equals -1 dark spot, M equals -2 dark spot. This is the single slit pattern. Now our condition here is that we want the double slit second order bright spot to be annihilated by the M equals 1 dark spot. Okay, so I'm going to have to try to fit this in then. Here's my double slit. This is going to be M equals 0 for the dark. Remember, these aren't the same M's. This is the M for the D sine theta equals M lambda over D. This is the plot for the D sine theta equals M lambda over A. So the M values aren't the same. And so there's M equals 0. There's M equals 1. So then there would be M equals 2. So that's what we want. We want M equals 2 to be annihilated by the M equals 1 dark spot. And then there'd be symmetry. So you'd have it over here too. This would be M equals -1. And this would be M equals -2. Then this would be M equals -1. So it would also be wiping out this pattern there. So what you'd see then, you'd see bright spot there, a bright spot there, a bright spot there, then nothing. Then you'd see a less bright spot here because the overall intensity of the single slit pattern is dropping. Okay, and so that's wiping out the intensity here too, as well as, so that's less bright, less bright, less bright, and then nothing, and even less bright out here. And then out here, nothing, and here, similarly, kind of symmetric, then nothing there, and then even less bright out there. So that means that our data is all coming from in here. Does everybody see what I'm representing by this? Anybody have a question about it? Because if you don't have the picture, then it's not going to help for me to just write an equation. Yeah.
Where you have d sine theta equals m lambda over d, is the d on the left-hand side of both those equations not
I'm sorry, this should have been signed. I'm sorry. Should have been signed. Thank you. All right, so what do we do then? Well, we want to set up an equation so that the sine of theta is m lambda over d. That's going to be m prime lambda over a. So the m here is going to be 2, and the m prime here is going to be 1. And we want the angles to be the same, so that means the sines of the angles will be the same. So that looks really simple, doesn't it? That's an easy equation. The lambdas cancel, and so what do we get then? We just get A is equal to D over 2. How much easier of a, that's like just a basic high school math problem. There's nothing to it. But understanding what is meant by this statement and being able to draw a figure which represents it is where the real physics is located in this problem. But the math, again, isn't that bad. Question?
How exactly do you know that n equals 2 has to match up with n equals 1 of the two different ones?
Because I wanted to wipe it out. So that's what's happening here. The m equals 2 is being wiped out by the m equals 1 dark spot. Mark?
Is this an exam question or quiz question?
Quiz? Yeah, I've asked this before in quizzes. Maybe an exam. Yeah, possible. I mean, it's simple enough, you know. And then if I ask you to draw the thing, a lot of people could just memorize an equation like that, but then understanding how to draw it. So that'd probably be what's happening. The problem is this drawing the thing out properly. Any other questions? Okay, so that's our single slit. What about, I know this question is coming, what about diffraction around a circular aperture? That's the next thing. Okay, now if we have a instead of having an aperture that's just a one-dimensional slit, what if this were a circular aperture? When would this be the case? Well, in your eye, there you have a circular aperture that lets through light in the pupil, okay? And so what kind of an interference pattern do we get because of the fact that we have a circular aperture instead of a slit, which is a one-dimensional aperture opening? And the answer is you get these same kind of patterns. This is the central interference maximum. This is the m equals 1 dark spot. This is the m equals 2 dark spot. M equals 3 dark spot. And guess what? Our brain is ignoring all of that information all the time. So we have light coming in, it's producing this kind of a pattern, but that would just kind of, whoa, look at all of these circles around circles, and then the tiger comes in and eats you, and that is wiped out of the gene pool. Okay, and so we ignore everything but the central interference maximum because it's just would be a distraction for survival. But all of these things are in there. And it's coming into our brain. Our brain has a computer program that says ignore all of those bright bands. So if we change the light, notice here if we go to lower wavelength light like red, notice that it gets bigger. The pattern is getting bigger because this goes like m lambda over d type of thing. Right? So lambda gets bigger, that means that the angles get bigger. And so the thing gets larger. And so this is the single slit diffraction pattern through a circular aperture for red light. And then this is for blue light, quite a bit smaller pattern. But they're all basically the same idea. So if we are looking at something like this, then this also affects our ability to see really small objects. Let's just go like that. Okay, so if you have two objects that are separated by a certain distance, at first, the central interference maxima don't overlap. that as you get to closer and closer angles, they do start to overlap. So that's what happens here. Okay, and so at this point then, you can't tell the difference between one and the other. And so this affects how small of an object you can see. Even if you have an infinite number of retina cells, you're not going to be able to see bacteria. Okay? Because the aperture is too small in your eye. So you go, well, let's just make the eye bigger. So you make the eyes the size of trash can lids, then you could even see X-ray separations. Now that would be really cool. You could forget about the 5-second rule or the 2-second rule. You could just look and see whether something has bacteria on it, and you can wash your hands, and you wouldn't need to if it didn't. So that seems like it would be a great survival mechanism. But the problem is that if you had eyes that big, that would be quite a liability if you got into a fight with another creature. And so, again, that was taken out of the gene pool, that thing with big eyes. And also, there's a lot invested in terms of evolutionary energy in really huge eyes. And is that worth the telltale evidence that you could get for disease? And then would creatures that don't have enough brain capacity be able to recognize that as being a sign for disease? But anyway, we have this limitation, and this limitation is due to diffraction around a circular aperture. And so here we can see how the single slit pattern from this light source lines up like this. The single slit from this pattern lines up like this. And so we can see the two as being separate. But eventually, when the central interference maxima get too close together, then you can't tell them apart anymore. And so that's the same thing with stars. You know, let's say you have a double star system that's far enough away, you might not be able to tell the difference between the two stars. They would melt together. Or if you had a planet going around a star, that would be even worse. And the planet's not putting out much light, but its single slit pattern coming in at a slightly different angle from the star as it's orbiting around it, we just merge together. And so the criteria then for resolving two separate images with a circular aperture is sine theta minimum. So this is the minimum angular distance before they start to merge together. This is equal to 1.22 lambda over d, where d is the diameter of the circular aperture, and the 1.22 is a correction factor because we're dealing with something that has two dimensions with spatial symmetry. But the criteria for being able to resolve these is that you need to have the minimum from the first and the maximum from the second no closer than that. Okay, so in other words, when the m=1 minimum lines up with the m=1 maximum, then that corresponds to your theta minimum. And that's called the Rayleigh criterion. And so when you do the math, and this turns out to be a little bit sophisticated to get the 1.22, but you end up with this relationship. So there's no m value in here because what you're doing is satisfying the Rayleigh criteria, and by doing that you're finding the minimum angle that can be resolved so that you can tell the difference between one object and the other. So that in this last picture here, you can tell the difference, but when they merge together, you can't. Okay, so you can tell the difference here, that if you brought them closer together in that other picture that I showed you, it would look like this. Now you can't tell the difference between them anymore, and you can't resolve them as separate objects. So let's check this out for a particular problem. Let's say that we have say we want to be able to, okay, so here we've gone too far. And here we want to see, well, what's the diameter of the circular aperture that will allow for resolution of a certain height newsprint. Okay, so let's say that we have the ability to have an infinite number of retina cells available so that we don't have to worry about resolution of the image. We just want to look at the effects that are due to single slit diffraction around a circular aperture. Let's ask, what is the height of newsprint that can be resolved by an aperture diameter of 2 millimeters? So let's say your eyes are dilated, you have an aperture diameter of your eyes of 2 millimeters, and you want to read the height of newsprint from, let's say, our standard 25 centimeter away distance. So how do we draw a picture for that? Well, you could say that this height here of the newsprint is y. This distance here, L, you could call 25 centimeters. This is definitely small angle approximation, so you can say the sine of theta is approximately the tangent of theta. Now that wasn't true with our single slit stuff. When we looked at single slit and multiple slit, we can't make this assumption because the angles are greater than 10 degrees. But here, the angles are going to be much less than 10 degrees because we're looking for the minimum height of the newsprint. So we're looking at angles maybe a fraction of a degree. Okay, and so if we do this then, this is not a flower but a newsprint at 25 centimeters away, then the tangent of L is, or tangent of theta is y over L. So that would be equal to 1.22 lambda over d. So what's lambda? Well, you've got anywhere between 400 and 700 nanometers, and so let's just get an idea of an average wavelength. Realize there's going to be a little bit of a variation here. It'll vary by almost a factor of 2/7/4, right? Because you can go from 400 to 700. but let's just use 500 for a typical wavelength. Nanometers. So then we just solve this. Y is a simple equation again. 1.22 times lambda. So you wouldn't be putting in 500 here. You'd be putting in what?
500 times 7.
Good. 500 times 10 to the minus 9, or 5 times 10 to the minus 7 meters. Okay, so that'd be 1.22 times 5 times 10 to the minus 7 meters. And then the diameter of the pupil is 2 millimeters. You're not going to put in 2 here, right? 2 times 10 to the minus 3 meters. You see so many of these errors, especially in multiple choice questions. That's awful that you're losing all of the points for not doing the unit conversion. It doesn't need to happen. Okay, so here, then that's going to be times L. So L is 0.25 meters. So let's knock that number out. So that's giving me 7.6 times 10 to the minus 5 meters, or 0.076 millimeters. Okay, now it turns out that if you had infinite resolving power, you might be able to see something that is on the order of double this. Okay? If you didn't have any problem with getting that amount of light, and if, say, you had a huge number of retina cells, you could probably see something that's about twice as high. But it wouldn't make sense to invest a lot more energy in retina cells if you're only going to get a factor of 2 more than what you can get from the minimum limitation of single slit diffraction. And so if you want to see something smaller then, what do we need to do?
Increase aperture diameter?
Good. The aperture diameter has to go up. And so to try to tell the difference between one, say, star and a planet, what you need is a gigantic aperture diameter for your telescope. And if you do that, then you can see much smaller angles. And if you can resolve those smaller angles, then it might look more like this again. And so that's what you want then. You want to be able to, if you're looking for very, like, looking for Earth-type planets or whatever, you would want a big aperture diameter, not just to get in more light to resolve the image better, but also to help alleviate some of these problems that are associated with single slit diffraction about a circular diameter. Okay, so that's pretty much it for the different applications that I wanted to look at least for the moment, for diffraction. Are there any questions about this? Okay, the next topic then is thin film interference, and this actually comes from an earlier chapter.